Bismillah ar-Rahman ar-Rahim. So we started talking about the very important and fundamental. Very important and fundamental matrix that we use to evaluate the performance of any end-to-end session or a network. So we discussed first the delay, and we divided the delay into 4 components, like processing delay and queuing delay and so on. And we discussed each individual delay component. We also started talking about packet loss. So packet loss when the queue inside a specific router is full and you send a packet to this router, so the router will have to drop the packet. And we said that dropping this packet does not mean that the packet will never reach the receiver. So if you use any reliable protocol from the transport layer point of view, you can retransmit this packet again. So in assignment 1, you will get to really calculate these values, which is very important. It's posted already on Blackboard. I'm not sure if you noticed. So you will get to calculate these values as part of the simulation. And it's very important to know how to calculate each of these matrix, because these are the fundamental matrix that we use to evaluate the performance of any routing protocol, any transport protocol, any protocol in the network. So today we'll start talking about the throughput, and the throughput is a very important metric that calculates the rate in terms of bits per time unit. Time unit is mainly a second, so bits per second. So how many bits per second is transferred between the sender and the receiver, end to end, okay? So this is very important, and this throughput is based on so many factors. It's based on the sending rate, but the sending rate is not enough to calculate the throughput, okay? Just the fact that the sender is sending with a specific rate, that doesn't mean that the receiver will receive it with the same rate. So this is a very important issue now, okay? So there is the sending rate, and there is also the rate which is dictated by the virtual pipe that connects the source with a specific intermediate device in the network, like a router or a switch or something. Okay, so between the sender and each intermediate device, there is a pipe, there is a virtual pipe. Okay, so the data rate that this pipe offers to this session dictates the throughput, or it affects the throughput between the sender and the receiver. And this is a complicated way, because these pipes are not homogeneous. They don't have the same radius per se. So between the sender and the receiver, you might pass through an Ethernet link, and then pass through a wireless link, and then pass through a fiber optic link, and so on. Right? These are logically represented by a different radius of the virtual pipe between the sender and each intermediate device. Okay? So it's like you are injecting or flowing a fluid from the sender to these pipes. So the bigger the radius is, the more amount of fluid that you can feed into this pipe. But if you have like a bigger pipe and then the pipe gets smaller, then you are restricted with the bottleneck part of this end-to-end link. That's why the throughput is a bottleneck metric. They call it a bottleneck metric. So the end-to-end throughput is affected by the minimum rate on each intermediate link. Whereas delay, they call it an accumulated metric. the delay, is accumulated metric, which means that the delay of each intermediate link gets accumulated to the end-to-end delay. So there is a big difference between the two. Okay? Loss is also either accumulated or they call it probabilistic. We'll talk about that. So if you have, between the sender and the receiver, if you happen to have two pipes like this, one offers a data rate of RS and one is offering a data rate of RC, what is the throughput end to end? The minimum of RS and RC. بالضبط. The minimum of RS and RC. And actually, I should include also the sending rate, because maybe the pipe is offering you a specific data rate, but the application is not utilizing this pipe efficiently. The application wants to send with a data rate that's less than both. That's fine. It's by choice, and in that case, the throughput will be dictated by the sending rate from the sender. So it's basically throughput is the minimum rate along the end-to-end path. Okay. So there are two types of this throughput. There is the instantaneous throughput or the average throughput. So the instantaneous throughput has a significance as at a specific time instance. So at this instance of time, the throughput is that much, which is, so there is the throughput versus time. So this is the throughput. And it could be like something like this. Okay? So this means that at this point in time, the amount of bits per second that you can send from the sender to the receiver is this much. Why is it dynamic? Why is it going up and down? Well, this is because of what? The different records. Yeah, there are so many factors that affect the variability of this throughput. The queuing time at each intermediate router. If you have wireless, then the channel dynamics affect the amount of bit rates that you can send over this channel. So there are multiple factors. So in reality, the throughput is a variable in instantaneous fashion, is a variable metric. It goes up and down. Okay? Whereas the average throughput is the average of this altogether. So the average is like you get a simulation time or a running time of maybe like 10 seconds, and you get the average throughput across the entire time duration. So basically, you calculate the amount of bits, like within 10 seconds, you calculate the amount of bits that the receiver receives during the entire 10 bits, the entire 10-bit duration. And then you divide the amount of bits by the 10 seconds, you get the average throughput. The instantaneous throughput, in order to calculate the instantaneous throughput, some people, they take a very small, tiny little window, not like 10 seconds. You use like, let's say, maybe half a second or maybe 0.1 second or something like this. Okay? So within this 0.1 second, you calculate the amount of bits you can transfer end to end, and you divide this over the 0.1 second. So this gives you, so at 0.1, you calculate the amount of bits transferred from 0 to 0.1. And then you divide this by 0.1, which means you multiply by 10, and then you put this value here. And then you go another like 0.1 second, you calculate the amount of bits, and so on. So this way you can connect these dots and form this curve. Okay? So the average is nothing but you enlarge the duration of time, like 10 seconds or more, and then you calculate the amount of bits during this time. So if it's a small window, it's instantaneous. If it's a very large window, it's average. Okay. طيب. So the average end-to-end throughput, if RS is less than RC, we said that this is a bottleneck thing. So the throughput will be, the average throughput will be dictated by RC. Okay, so assuming that the sender is sending and utilizing this pipe efficiently, which means that I utilize all the bit rate that this pipe gives me. So in that case, I can inject amount of fluid equal to RS. So in that case, the average throughput will be RS. If RS is greater, in that case, the amount of fluid that I can inject in this is big, but the end-to-end rate will be dictated by this link in that case, and in that case, it will be RC. Which means that the bandwidth, or sorry, the throughput, end-to-end is a bottleneck matrix. So the link is divided by, the link throughput is the minimum of the two data rates. طبعا if I have like, let's say 10 clients and 10 servers like this, and all are sharing one link, okay? So of course, if I want to calculate the throughput of each end-to-end link, assuming that this rate will be shared amongst the 10 clients fairly, which is typically dedicated, or sorry, it's typically guaranteed by TCP. TCP provides fairness. One of the features of TCP is that it does provide fairness. So in that case, the average throughput of each end-to-end session will be dictated by, of course, RS or RC, whichever is smaller, or the shared rate across this shared link. This shared link is shared by 10 different sessions. If this link has a data rate, offers a collective or aggregate data rates of R, then the average rate given to each session is R over 10.
If it's divided equally, by the way.
If it's divided equally, man, that's what I'm saying. It's so if it's used fairly, that's what I mean by used fairly. If it's divided equally, which means there is like some kind of fairness guarantees between these sessions, which typically the way for if you were to use مثلا TCP, unless of course you have مثلا ADSL here versus Ethernet access network on another session. So in that case, there may be lack of fairness in that case, but typically the shared link will be divided fairly between the sessions. So the end-to-end throughput of each individual session is dictated by either RS or RC or R over 10, assuming equal share for all the sessions. So the pair connection end-to-end throughput in that case will be the minimum of RC or RS or R over 10. So if this shared link is like a fiber optic link and you have a huge amount of bandwidth, then the throughput will be limited by the access network of each individual client, which means that it will not be limited by the core network. The core network is like fiber optic, and it's like it's a huge amount of bandwidth. So bandwidth is not an issue in the core network, but it's an issue in the access network. So it's either the access network of the sender or the access network of the receiver. Maybe the sender is sending huge amount of information, and in the core network it's flowing with no delay whatsoever, but the problem is the access network of the receiver, right? So in that case, you're sending huge amount of traffic, but the receiver cannot cope with this huge amount of traffic, so it will ask you to slow down. And that's what TCP does. We'll talk about this. Flow control, not congestion control. Okay? Congestion control is from the network point of view. We'll talk about the difference between the two. So on the other side, if the core network is limited, then R over 10 will be the limiting factor in that case, not RC or RS, not the access network. Go ahead.
This assumes also that all the servers are transmitting at the same time.
The clients.
100%.
The servers are. I'm sorry. Okay.
All the users or
Right.
are transmitting at 100% of the time. So
right.
If it is less, we return back to the
that's what we said. But yeah, that's what we said. If the access network is offering this pipe, and the application chooses not to use all the rate provided by this pipe and chooses to lower the data rate, then there is like an R sending rate. Okay, so you are not utilizing the pipe provided to you, you are utilizing less than this, it's by choice, then the throughput will also be dictated or limited by the sending rate. So, of course, the assumption here, just to simplify this, is to assume, as you said, that...
I mean the R over 10. I mean the R over 10.
Yes.
Yes. If this, so we are writing R over 10 because we are assuming that all the 10 users are transmitting at the
right.
same time. But because
not necessarily at the same time. Here, we're talking about average. Not we don't require any synchronization between the 10 sessions. They don't have to send at the same time. On the average, this is average. So they are sending with a rate which is maximum. If all of them are sending, not necessarily in a synchronized way, but if all of them have data to send, okay, and they send with a rate which is provided to them by the access network and by the core network, okay? And they are trying to utilize whatever rate provided to them by the access network or the core network, okay? But they always have data to send. Otherwise, you are establishing a session end-to-end and you're not utilizing it. So you're wasting bandwidth. You're wasting resources in that case. But if you always have data to send, and you are consuming the rate provided to you by the access network and or the core network, then this will hold true on the average, without any restrictions on the synchronization between. They don't have to send together. They can just send independently, but on the average, the core network will give them a fair share. Okay? There is a fair share that will be given to them. In practice, this is this is not necessarily true in all cases. Like nowadays, the access networks are relatively fast, especially if you have fiber to the home technologies or something. More often than not, the data rates are limited by the core network. The service provider, we have very fast access network, but the service provider limits the data rate provided to your home network, right? Based on certain agreement or something like this. So in that case, this will not hold true. The bottleneck is in the core network, not in the access network. But in many cases, it's limited by the access network. Regardless, it's the minimum of the data rate on the access network and the core network. But the core network typically, the main issue here is that the core network rates typically are shared fairly between the end-to-end sessions, unless, of course, you're using some kind of a quality of service. If you have specific quality of service differentiation between these users, then, which is the topic that Habir covered last time, so in that case, the core network may choose to give data rate to one user more than the other, on purpose. In that case, the average throughput, the average data rate provided to each end-to-end connection may not be R/10 in that case. Maybe something different depending on the characteristic of the application, whether it's a video application, text application, graphics application, and so on. Okay, any questions? So the last topic in this chapter is what we call protocol layers or service models, and that part talks about the fact that in order for us to design the protocols in the network, in the internet network architecture nowadays, we can find, due to all the issues discussed before, that it's highly complex. The network function is highly complex in the sense that it's very confusing, or it's very difficult, or it's very hard to comprehend the fact that we talk about it as one unit. We have to really divide it into layers or certain structure in order to be able to simplify the discussion and make it more modular, and we can deal with it. So, so as we said, that there are some intermediate devices in the network, and there are links and applications, protocols, hardware, software, all these things, and networks are inherently very complex. So is there any way or hope to organize the structure of the network, or at least simplify the discussion of these network issues? And the answer in many cases is that we have to use some kind of layers. And this slide here discusses or mentions an analogy with the real life that we have. So, so luckily I have disabled this annoying feature, finally, alhamdulillah. So, so the analogy here is that imagine that someone is traveling. Someone is traveling is very much similar to one packet is going through the network. So, so now I am on the packet. So if I were to travel, first I have to purchase the ticket, and then after purchasing the ticket, I have to go to the airport, use the baggage, or do the baggage check-in, and then go to the gates, and then from the gates I have to get to the airplane, and the airplane goes through the runway, and then from the runway the airplane will go through the air, and then here we're talking about some intermediate airports or intermediate points where the airplane may actually land in a specific airport, and whether you get to go out of the airplane, or maybe there is a transit that you don't have to get out of the airplane. So it's very much similar. So if you were to get out of the airplane, which means that you have to recheck in, which is similar to the fact that we have to recreate the packet again in a specific intermediate points. Whether you have a switch. So whether you have a switch, in which case you will not get out of the airplane, you will stay, but you may actually change the airplane in the same airport, or you may have to go to the gate, which means that you get rerouted to another route, which is similar to the fact that the packet goes into the routing layer. Okay, so here you may actually have some layer depending on whether you get out of the airplane and you go to the gate and reroute yourself, or or in some cases you have to recheck in, you have to reload your baggage and so on in intermediate points. Okay, and then you have to go to the airplane again and go and fly and go to the runway and repeat the same process until you reach to the arriving airport, which means that you have to do the reverse operation of what you did here all together until you arrive to your final destination. So this is in fact very much similar to the network function. We also need to divide the network functionality into layers, and this will have enormous benefit on multiple things, which we will talk about. I also have to mention here is that, of course, at each layer, we have to implement certain service. So here we have to do a ticketing service. We have to do baggage service. And the good thing about this is that, well, first of all, there is a logical type of horizontal communication between each layer. So the ticketing on both sides, they sort of communicate implicitly between each other without really knowing what's underneath. They don't have to know the details about what happens at the gate or what happens at the runway. They don't care. Okay? So at each of these stages, there is a certain service or set of services that get provided by this layer without really having any knowledge about the other layer. And that allows to have logical end-to-end or layer-to-layer communication, and at the same time have transparency or no knowledge whatsoever about the underneath layers. So that's one thing. The other thing here is that this structure allows us to change the process of at any layer, at any point in time, without affecting the upper and lower layers. So I can choose to enhance or modify the baggage claim. Instead of, I can renovate, for example, the escalators or something, or I can enhance the process of how you get your baggage, and that will not affect the ticketing service, and it will not affect how you find your gates and stuff like that. Okay, so I can choose to modify a certain level of the network without really being affected or without affecting the upper and lower layers. And that creates a structured and more modular design for the network, which on one hand, it simplifies the discussion. So we can certainly divide the chapters that we will discuss based on the layers, which makes sense. So in each chapter, we will confine ourselves to the concepts and services provided in this layer. For example, when we talk about transport layer, we will often call the data units segments. So we know when you say segment, it's transport layer. When we get to the routing layer, we will talk about packets. So when we say the word packets, we know that we're talking in the routing layer. So there is some terminology and concepts which are confined in certain layers, which really simplifies the discussion. The modular design also creates some kind of competitive environment, which means that I can ask a subcontractor to design a new baggage service, okay? And you can have a subcontractor or a vendor that really is specialized in this part, rather than just having all the network function as one unit. So you cannot have really a small company to provide a specific network function because it's not well structured. If it's structured in a modular design like this, you can have a third party or a vendor which is specialized in a specific function. And they can perfect this function without really knowing anything about any other service in any other layer. So that really promotes the competitiveness of providing services in the internet. So that's why you have Microsoft. Microsoft has nothing to do with turbo encoders or turbo decoders, or they don't really work on physical layer issues. They don't design transceivers. They don't really design مثلا routing protocols. They are not specialized in these domains. And in many cases, all the routing protocols in Windows and stuff, they more often than not, they buy it from third party and they just put it in the operating system. They don't really have to work in this domain. But the modular structure defines what we call an interface. An interface is a point of operation that really governs the communication between one layer and the layer underneath or the layer above. This interface is very important. It's like exactly when you call a function in C++ or Java. The interface is basically the function header. The function header defines a specific API and set of parameters. Okay? The body of the function defines the procedures or the services provided by this layer. So you can change the body of the function. As long as you don't change the API and the set of parameters, the interface to the layer is the same. Right? So the interface is the same. I can call this function to do this or that. It doesn't matter to me as long as I'm calling the function with the right set of parameters. So this is the interface. And that's very important. As long as the interface is the same, I don't care whether the body of the function changes or not. You see what I mean? So this is a very important concept. So now I can call a device or a specific function which is implemented by Microsoft or Cisco or Google or whatever, as long as the interface is the same, I don't care whether I'm calling this function from this vendor or that vendor. So that promotes the concept of competitiveness. So that really unleashes the limits for different companies to come up with optimized implementations and set of protocols, and as long as these interfaces are fixed and agreed upon, they can do whatever they want. Okay, so that's a very important concept. So modular design simplifies or the structured design simplifies the discussion, and it promotes competitiveness, and it creates some kind of seamless design between these layers, and it allows me and gives me the flexibility of changing the functionality within a specific layer without affecting all the other layers. So all these issues are very important. That answers the question of why layering. I should also mention that despite all these benefits, some people argue, especially nowadays, that this layer design is not valid anymore. So is there any disadvantage to the concept of layering? Yes. Yes. For example, in many cases, we have to replicate the same service in two different layers. For example, we have TCP in the transport layer that provides reliability, right? That doesn't mean that in Ethernet we don't have reliability. We have to have reliability between each two nodes in Ethernet or network access layer, in addition to TCP. So in many cases, we have to provide or we have to replicate services in multiple layers, because each layer is independent from all the other layers. The other thing is that in many cases, if you want to have good performance, and that's maybe will be covered by Khaled today, if you want to have good performance, in many cases, higher layers, they need some information from the lower layers in order to perform more efficiently, which violates the concept of layering, because we said that layers are independent. They are supposed to be independent. But in order for you to, for example, perform flow control in TCP in an efficient way, you may have to have some information from lower layers. You know, for example, مثلا TCP over wireless can behave very badly if you don't have the channel condition. And in wireless, the channel is really dynamic, and it goes up and down. In some cases, very fast. And TCP cannot cope with that. So TCP will perform very badly if it does not have the proper information from the MAC layer and the physical layer. Okay? And in order for you to get the information from lower layers, that violates the concept of layering. Okay? So that's why people argue nowadays that the layer design is not the most efficient way, and in many cases we have to violate it. Another big example, which has started to be a very emerging and a very hot topic nowadays, is what we call software-defined networking. So software-defined networking is one of the major concepts that are emerging nowadays to provide huge amount of opportunities for people to do research. The idea is that this modular design is not good anymore, because nowadays, one way of structuring this is because of the fact that we have limited computational functionality, and we have to implement some layers in software and some layers in hardware, and we have to have very structured design. Well, nowadays we have clouds, we have a huge amount of facilities that we can leverage in order to provide very sophisticated computational capabilities, right, without having any limitation. So the idea of software-defined networking is to say, well, these protocols provide some control or some procedure to govern how the packet will be sent over the network. Well, we will isolate the control or these procedures from the way that the packet is being transferred over the network. We will push these protocols to be done in the cloud, purely in software. So this actually isolates the data plane from the control plane. The control plane is where all the procedures are being run. And the data plane is where the packets actually flow over the network. Okay? So the idea here is that I don't really have to have distributed routers and switches and so on and so forth. No, well, the router can be very simple. And all the logic of the router to decide how to route the packet is in the cloud. Okay? So this fundamental change is very drastic, because now, for the packet to move from one place to another, it has the router really does not perform any local computations. It has to connect to the cloud. It has to connect to a specific network controller, and the network controller will tell it where to go. Of course, there is some issue with that, and nowadays they are talking about enhancing this and so on and so forth. But the idea here is that the data plane is as usual, but the control plane is centralized. Centralized meaning that this allows you to get whatever information you want from this layer or that layer without having any limitation. And leveraging the computational capability of the cloud, the argument is that you can enhance the performance drastically using the concept of software-defined networking. But while doing that, we are violating all types of standards that we know of nowadays. It's not standard-based. Software-defined networking is a revolutionary approach that kind of wipes out all the existing standards, and it has to be redesigned or rethought of from the beginning. There is quite a bit of fight between software-defined networking community and IETF community or internet community to to debate and whether this is good or bad for network performance. But this is one of the concepts that really violates layering fundamentally, and it creates a lot of discussions nowadays. So going back to our structured and our layered design, using this layered design, we have the concept of encapsulation. And encapsulation cannot be really described in the same example we talked about. We don't really encapsulate ourselves, but you can understand it well if you talk about مثلا sending a letter through mail. So it's like you have to encapsulation talks about the fact that from the moment you create the letter, you have to put it in one envelope, and then you go into each layer and you have to put it in certain envelopes that add some information to how you can process this packet from one endpoint to another. So encapsulation talks about the fact that in each layer you have what we call protocol data units. Protocol data unit is a data unit which defines the information unit in a certain layer. For example, protocol data unit in transport layer is called a segment. A segment is transport layer protocol data unit. Packet is routing layer protocol data unit. Frame is data link layer protocol data unit. Okay, so and this in each layer it adds a header, and the header is a set of fields which define certain values that gets processed and interpreted by a specific protocol in that layer. As part of this header, you have to also give some information, which we will talk about the protocol in the upper layer. Okay, so you have to also provide like pointer to which protocol in the upper layer. Because, for example, مثلا in routing layer, you need to, here, when the information flow all the way and it gets here, okay? So when you go up in each layer you have multiple protocols. مثلا from the routing layer to the transport layer. What tells me that this is like a TCP or UDP? So there's something in the IP packet that tells me whether to invoke UDP or to invoke TCP. So it's like a pointer to the upper layer, because these routing protocols, they run as processes, as software processes in each layer on the router or on the host. They run as specific processes. So from one layer to another, you have to really put the information unit on the buffer of a specific process, whether IP or other protocols in the routing layer, whether TCP or UDP, and so on, whether on FTP or HTTP or Telnet or something like that in the application layer. So in each layer there has to be. So encapsulation is easy because you put things inside, but the decapsulation you have to tell me when I get it out, what protocol needs to be invoked in order to process these packets. Okay, so we'll talk about that. So this is encapsulation and this is a decapsulation. So that decapsulation is also a very important concept. So in summary, we have discussed these issues. We have discussed the internet overview, what's a protocol, the network edge, access, core network, and so on. Discussed packet switching, circuit switching, the internet architecture, the performance metrics. Okay, and we discussed the layer service. So, of course, this introduction provides like a global picture, but the picture is hazy. And our job from now on is just to get at each part of this picture and get more clarity and try to put more clarity on that part so that we can see the global picture in a higher quality. That's what this means. The introduction covers everything, but we covered different concepts in different layers. So now we will go at each layer, and then we will shed more light on this layer to start talking about the terminology, the concepts in this layer in a more depth. Okay? So we'll break here. Okay, so in chapter 3, we'll talk about the transport layer. The goal here is to understand the principle behind the transport layers, as we might have encountered before. There is the concept of multiplexing and demultiplexing, how TCP multiplexes different sessions from the applications to the network, and how how TCP or how the transport layer protocol provides demultiplexing, which means that it sends the segment from the transport layer to one of the applications running in the application layer. Whether or not the protocol provides reliable data transfer, whether or not it provides flow control, and what does flow control means, and congestion control. Of course, we will apply these fundamental concepts into specific examples of protocols in the transport layer. Of course, UDP as an example of connectionless transport layer protocol. We talked about connectionless before. The idea is that you don't have to establish an end-to-end virtual pipe between the two endpoints, or TCP, which provides connection-oriented, in which case you have to establish a session first, you have to establish an end-to-end connection first, in which you have to incur certain delays to establish that connection. But once you establish this connection, this gives you the ability to provide better quality of service in terms of ordered packets and so on and so forth. You can provide flow control on this end-to-end session. You can provide congestion control on this particular end-to-end session, and so on. So transport layer services, they provide logical communication between application endpoints, between two application endpoints. Okay, the endpoints is the interface between a certain application and the network. We call it an endpoint, which is specifically a port number, which is identified by a port number, and in many cases it's identified by a port number and IP address. Okay, so the transport layer protocol provides the logical end-to-end communication between two transport layer protocols, and it maps or interfaces the application to the network. Particularly, the transport layer protocols, they divide the application information into segments. These segments, they get sent through these application endpoints, which we call them طبعا which are represented in the network by the concept of sockets. So these segments will get sent across the sockets from one application endpoint to an end application endpoint. So these segments will be reassembled at the receiver side by the transport layer protocol first, and then it will get sent to the application layer. Whether this is a HTTP application or Telnet application or FTP application and so on. Of course, more than one transport layer protocol are available in the internet. Of course, there are tons of protocols other than TCP and UDP, but these are the most common protocols. These are, and of course, by far, the predominant one is TCP. Even with all the issues with wireless and stuff, but still, this is the predominant protocol used on the internet. So we'll talk about both. We'll talk about TCP and UDP and the difference between them. So, so the most important service which is provided by the transport layer protocol, and this is provided by all transport layer protocols, TCP, UDP, RTP, whatever transport layer protocol you talk about, the minimum it has to provide is multiplexing and demultiplexing. So what does that mean? This means that if you have two applications running on two different hosts, two remote hosts, okay, and they try to communicate with a specific host or server. So you can think of this as a client 1, and this is client 2, and this is server, which serves both clients. Okay? So multiplexing in that case talks about the fact that the segments will be sent through this endpoint, and this is what we call a socket. So the application has a process. A process is a piece of hardware, a piece of software that runs on the host. And this software represents a network application, like مثلا web browser, like FTP client, anything. So each of these applications run as a process, as a separate process on the host, and they use a socket to interface with the transport layer. This socket provides the interface between the application and the network. Okay? In many cases, the application has control to the socket in a limited way. So the application has the control to specify a specific transport layer protocol as part of the socket. So you can create a TCP socket or UDP socket. Okay? So for that, the application has access or has the choice to create a TCP socket or UDP socket. In limited cases, you also have limited access to certain parameters in the transport layer, like the buffer size or something like this. But you have no control whatsoever from the socket on how the transport layer functionality is conducted. For example, how flow control is performed, how congestion control is performed. Socket does not give you any access to this. Okay? So this is pure functionality inside the transport layer, which application does not have access to. So the socket is the interface, and it provides like some interface points, like you can select the protocol, or you can select or set certain parameters in like the buffer size or something. Other than that, you cannot have any control. So if you have multiple applications here, so you have P2, you have P1, and so on. So these applications each will have different sockets. Each socket is identified by a specific, well, I should say, you can either have individual sockets or one shared socket, depending on whether you use UDP or TCP. For TCP, you will always use individual sockets for each application endpoint, even if you are using the same port. So even if two applications are trying to access the same port, they may actually create two different sockets because they are communicating with a different server. Okay? For UDP, if you are communicating through the same port, you will use one socket. So the socket is identified by only the port number. That's it. So UDP socket is defined by the port number only, regardless of what source address you have or what destination address you're trying to communicate with. So in many cases, for UDP, as we will see, you create a shared socket. So this is multiplexing. So you multiplex the segments in different sockets and send it to the transport layer. The transport layer will then provide certain services, which we will talk about in terms of flow control, reliability, congestion control, and so on. Okay, that we will talk about. And then you send this to the server. The server will receive the segments at the transport layer. So you will receive different segments. So demultiplexing talks about the fact that from the segment itself, you need to know which socket you should send it to. This is demultiplexing. Okay? So for that, the segment has to tell you whether, well, of course, the transport layer protocol that picks up this segment is identified by or from the network layer. So the network layer will have to put this packet on UDP process or TCP process. So UDP will pick up the segment and then it will say, how many sockets do I have and which socket should I send this datagram to or this segment to? And it knows that through what? Through what? What information is in the segment that tells the transport layer protocol which socket it should send this to? What piece of information I have in the segment that tells me which socket I should send this segment to? So should I send it here or here? Based on what? Based on supposed to be an easy question. Based on what? Based on the port. Based on the port. Port number. So the port number is the application identifier that tells me which application really needs to process this segment. Based on the port number, I will demultiplex or I will send this segment to one socket or the other. Once you put it on this socket, the application will then pick it up and start processing the data. Okay? So it's very important to know the demultiplexing happens through the port number. The port number is the main identifier for a certain application point. Okay? So this is the client. This is the client one application, and this is the server one application. So on this server, you have two server processes, right? So for example, this application wants to connect to an FTP server. So P1 here is an FTP server. This application wants to communicate with a web server. So this P2 is a web server. Okay? Or maybe both applications want to communicate with the same server. Okay? If both applications want to send to the same server, well, now it depends which protocol we're talking about. If we're talking about UDP, then we will use a shared socket. Okay, so the web server will be listening on a specific port, which is port A. 80. Port 80. Okay. Port 80. Okay? And it will use one socket on port 80 for UDP. UDP socket port 80. That's it. It's one. UDP socket port 80 is 1. If it's TCP, now depends. Because TCP is identified not only by the port number, but port number, source address, source port number, and destination address. So a socket in TCP is defined by 4 pieces of information: source port, source address, destination port, destination address. If you change any of these 4, it's a different socket. That's TCP. Okay? So this is multiplexing and demultiplexing. So multiplexing talks about the delivering the received segment to the correct socket. So I'm sending the application to a specific socket based on which port number and what destination address I need to communicate with. Demultiplexing talks about the fact that we have to route, or we have to, not route, we have to send the segment to the proper socket based on, again, the information in this segment. If it's UDP, we need only port number to identify which socket we send it to. If we need TCP, then we need 4 pieces of information. Okay? So that's demultiplexing and demultiplexing. So in the segment, we have the source port number, we have destination port number, and this is the header of any transport layer protocol. You have the minimum 2 pieces of information is source port number and destination port number. This has to be there, okay? Depending on what protocol we're talking about, these other header fields may be more or less depending on whether we're talking about UDP or TCP. And then you have the application data. Of course, this is an encapsulated segment or encapsulated protocol data unit in the transport layer level. Okay? So this is the header, this part is the header, and this part is the data. So this is header, and this is data. So host receives the IP datagrams from the network layer, and each datagram has source IP address, destination IP address. So I need to specify based on the IP address and destination IP address whether I'm using UDP or TCP. If I'm using TCP, I need the IP address as well, because I need to identify the socket based on the 4 pieces of information: IP address and port number for both source and destination. Each datagram carries 1 transport layer segment. Each datagram carries 1 transport layer segment. Each segment has source and destination port numbers. Host uses the IP addresses and port numbers in general, unless we're talking about UDP, in which case you only need the destination port. That's it, to identify the socket you need to send the segment to. Okay? So there is connectionless demultiplexing. For connectionless demultiplexing, we did not establish any connection between a source and a destination. We don't have any end-to-end connection established. In which case we're talking about an orphan. You can think of it as an orphan datagram. It only has the destination port number. And any web server, مثلا, uses 1 UDP socket for all connections. There's no actually concept of connections. Because whether it's coming from source 1 or source 2 or source 100, I don't care. Because there is no end-to-end connection established, أصلا. It's connectionless. So as the word suggests, there is no connection end-to-end. Okay? A connection, once it's established, it gets identified by the source and the destination. Each side is defined or identified by 2 things: IP and port. So I have 4 things. So once I establish the connection end-to-end, which is the case for connection-oriented transport layer, in which case you need the 4 pieces of information. So in creating datagram socket, datagram is a connectionless socket. We create the socket only by instantiating an instance of datagram socket. And the only thing we specify in that case is a port number. That's it. So that identifies the socket. That's enough in the case of connectionless multiplexing and demultiplexing. Okay? So when creating datagram to send into UDP, socket must specify the destination IP address and the destination port number. When host receives UDP segment, it then checks the destination port number only. And based on that, it directs the UDP segment to the socket of this port. In that case, the transport layer and the network does not care where this datagram is coming from. Okay? In which case, each datagram is transferred over the network independently. They may arrive, they may take different routes, they may arrive at different times, they may be unordered, they may be lost. And in that case, you will not provide any reliability. There's no actual sequence of these datagrams that allows me to order or reorder the segments. So there's no identification or reliability of some sort in the case of datagrams. If these datagrams are unordered or they don't have any reliability, then the transport layer does not provide that service. But that doesn't mean that the application will not provide that service. So the application may actually define reliability and some services from the application layer and uses UDP from the transport layer. Okay? So just the fact that these services do not exist in a specific layer, it doesn't mean that the higher layer will not necessarily implement that service. So I can, in certain cases, choose to use UDP and provide certain level of reliability from the application level, if I choose to. Okay? And we'll talk about the reason. Why do I need to do that? I mean, if I need reliability, why can't I use TCP? My TCP is there. Why can't you use it? Okay? There are reasons that in some cases makes you actually use UDP and provide certain services from the application point of view rather than using TCP. Okay? So connectionless demultiplexing talks about the fact that, remember, that any connection in the transport layer is bidirectional. Any connection by default is bidirectional. So you have this direction. So in this direction, you specify a datagram. When you send a datagram, you specify the source port, destination port. Okay? So when you send this to the server or to the other side application, remember that here you have destination port, which is 6428. Here we have destination port, which is a 6428. صح? Which means that both of them, by default, will be sent to one socket on the server side. Okay? So because the datagram is sent using the destination port number only, regardless of the source port number, regardless of the IP address. مفهوم? Okay. Of course, why do I need to send the source port in that case? Yani, the question might come. If the only thing I need is the destination port to create or instantiate the datagram socket. In the datagram socket, I specify the destination port number, right? But when I send the segment, I send the destination port and the source port. In the header, we specified both. So why do I need the source port in that case?
Is it because the bidirectional?
عشان ال bidirectionality, because of bidirectionality. So anything you send, you need a response. And the response has to go back to the same application. Okay? So when you send back any response, it goes to the source port here becomes the destination port, and the destination port becomes the source port. In the reverse direction, they get reversed. So the source port is needed in the segment so that the end application or the server application, when it tries to send back the response, it sends back the response using the right destination port to send the reply. So it's a request reply type of transmission. Okay? And here, I don't have to specify any of these IP addresses at all. So here, IP address A, C, B, I didn't have to specify any of these addresses at all. In the connection-oriented demultiplexing, TCP socket is identified by the 4 tuple, or 4 pieces of information. Source address, source port, destination address, destination port. The receiver host uses all 4 values to direct segment to appropriate socket, which indicates that for TCP, I have to create a socket for every single combinations of all these 4. Once the source port or the source address changes, on the server side, I have to create a different socket. Okay? So there is, of course, a good side and bad side about this. The bad side, of course, is the fact that the number of sockets will grow very large. So for a server, the server has to create and has to maintain and manage large number of sockets for different clients that tries to connect to the server, which will end up being huge number, okay, which is very hard to manage. But on the bright side, I can now provide flow control and congestion control and probably like some quality of service and so on per connection. I can fine-tune per connection. I can control this session individually, independently from other sessions. Okay? I can accept or reject. I can lower the rate, increase the rate. I can do whatever, okay, based on each connection. So server host may support many simultaneous TCP sockets in that case. And in that case, if any of these 4 pieces of information change, I have to create and instantiate a different socket. Web server have different sockets for each connecting client, whether it's non-persistent or persistent. Of course, since we have skipped application layer, we don't know the difference between non-persistent and persistent. Basically, non-persistent talks about the non-persistent HTTP talks about the fact that the page itself is represented by different objects, right? So you have different objects on the web page, right? So non-persistent versus persistent talks about the fact that whether you create a TCP session per object or per page. Okay? So if you have a complete web page that has different objects, for example, like video stream, images, different images, and different text, and so on, each of these is an object. In HTTP, each of these is an object, right? So non-persistent talks about the fact that for each object, I create a different TCP connection. And once I deliver this object, this TCP will disconnect, will go away, and then I create another one, and so on. This is non-persistence. Non-persistent, which means that it's not persistent, it's not lasting. Yeah. Or persistent talks about the fact that the same TCP session can be used to transfer all objects at the same time. Okay? Of course, that affects the round-trip time and all of this. But from our side, what we need to worry about is the fact that how HTTP as an application level example uses TCP. Sometimes it creates one TCP session per object, or sometimes it creates one TCP session per page. Okay? So for connection-oriented, if you have one client like this, you have source port, destination port, source IP address and destination IP address, and whether you are talking about the fact that you have two applications on one side, so each of these will have to have different sockets at the server side, even if it's coming from the same host. And even as long as you are creating different application instances, maybe it's the same web browser, but you're opening different tabs. Each tab will get a different source port. You know that, of course. So the operating system will assign for each tab and for each new window, of course, a different source port, which gets assigned dynamically by the operating system. Okay? So the source port gets assigned by the operating system dynamically. There is a certain range of ports, which is called dynamic port range, that the operating system has the freedom to assign to any client or any application. There is well-known range of ports, like for example, port 80, معروف. Port 80 is well-known that it's for web servers. Port, for example, 25 is for telnet. Port 21 is for FTP, and so on. These are well-known ports. Other than that is like dynamic range. The operating system has the freedom to assign these dynamic range ports to any instant application. Okay? So maybe those P2 and P3, it's the same application like Google Chrome مثلا, or Explorer, Windows Explorer. But you have different tabs, معناها these are different application processes or different application endpoints. Okay? Which in that case, each one will have a different socket. And these different sockets have to have a corresponding socket at the server side. Because these two applications have different source port. So the source port here is different from here. Even if they are going to the same IP address and same port. But because they are on two different source ports, the socket here is different, corresponding to these sockets. Okay? مفهوم كده؟ Okay. So this is for connection-oriented demultiplexing. Of course, this is what's used by TCP, and the previous one is what's used by a UDP. Okay. So there is, of course, the concept of threaded. The web server may use one process, one shared process for all the sockets, and then it uses different threads for each application. This is a concept which is very commonly used, and especially on the server side. So the server has one process, one shared process, and then it instantiates a thread. A thread is a lower level compared to a process, right? So the operating system deals with a process as a higher level entity, and then it deals with threads as lower layer entity. So one process may have multiple threads. And the server, what the server does is that there is one common process of the server, and then this common process has a server socket which is listening on a specific port. Okay? One server socket listening on a specific port. Once I receive a call request on that port, I have to take this request and instantiate a new thread, and inside that thread, I will create a socket to communicate with that particular client using the 4 pieces of information we talked about. And give this socket to this thread, and the thread will run from this point on. So it's like I have one shared process, and then I have one thread for each client. This is from the application point of view. This is the most common method. Okay? So the server has the flexibility whether to instantiate a different processes to communicate with each client. Of course, this will be much more expensive. To instantiate a new process every time you have a new client, this is very expensive, right? And instantiating a new process from the operating system point of view is a very expensive process, because the process has its own buffer, its own handling. It has so many resources from the operating system point of view that it needs to establish and dismantle. Okay, but the more common method is just to have one shared process, and then for each client you have a thread. To instantiate and kill a thread is a much easier process and less expensive. So that's the common practice.
Did you say that different tabs have different
Source ports, yes.
Source ports. But so if you'd like to open an account, any account, let's say for example Gmail, an email or something, you cannot open two different accounts in 2 different tabs.
You cannot open 2 different accounts in 2 different tabs. This is a browser issue. Yeah. Okay.
But if you open it in a different browser, it will work. So if the differentiation is not done in the port number, what makes the difference between tabs or browsers?
Okay, we should have probably discussed the application issue. Has nothing to do. Account context has nothing to do with the transport layer or ports, or it does not have anything to do with how the transport layer works. Account is an application level issue between a user and a server of some sort.
It's a cookie that is preserved on the browser itself.
Yeah, well, whether a cookie or not a cookie, this is a different issue. Here we're not dealing with these issues at all, whether it's a cookie, it's account information, whatever. The browser on top of the transport layer and HTTP, it has some other components. It has many other components that handles these types of issues, and in some cases it can pass this information from one tab to another. But this has nothing to do with how the tab itself, as an application endpoint, communicates over the network. It communicates over the network using source port and destination port and source address and destination address, and what we have discussed here. The application context itself, whether it's a session information like account information or credit card information, and so on and so forth, the browser handles this, and it may pass it from one tab to another transparently or seamlessly from the source port and destination port and these things. These are totally different. Okay? A transport layer does not care whether the segment contains account information or credit card I don't care about this. I don't care. I care about how I will interface these segments and how I send it to the network. That's what I care about. Whether this contains account information, credit card information, or cookie or not cookie, I don't care. ماشي؟ مفهوم؟ Okay. So the multiplexing and demultiplexing are the basic fundamental functions that have to be provided by all types of protocols. And whether we're talking about connectionless or connection-oriented, that's when the other functions, which we will talk about now, will be valid or not. So for connectionless, I cannot provide any reliability or flow control or congestion control because I don't have a connection. Okay? يعني control the flow of what? Control the flow of the end-to-end connection. I don't have a connection. ماشي? But if I have a connection-oriented protocol, now I have the context of end-to-end connection. Only now I can say that, okay, I can provide some flow control or congestion control. So what these are is coming. So connection-oriented is provided by TCP, and the concept of reliability talks about that it's very important in application transport layer and link layers, even link layers, by the way. So link layers down, they provide some reliability as well. And that's one of the examples that we mentioned, that you may have to duplicate certain service in 2 different layers. So you have end-to-end reliability from TCP point of view, and you have to have point-to-point reliability from the data link layer point of view. We'll talk about that later.
But they are different.
Yeah, they are different, but you have to provide different reliability in different levels. But if I have one unit of network function, then I can call reliability, one service, which is provided by the network function, and that's it. But because we have layers, we have different levels of the same service provided in 2 different layers.
They're all reliability, it's okay, but for example, in the physical layer, you may correct the base.
Now this all thing is coming from the layered model. From the layered model point of view, what you are talking about is makes sense, and that's what we have learned so far. Okay, that's what we are used to. We have layers, and we have in router we have 3 layers. In host we have 7 layers or 5 layers. In switch we have 2 layers, and so on. We always talk about layers. But if we remove this concept and we talk about one network function, then router will have the same layers or the same network function like a host, like any other thing, in which case you provide reliability for once, and you provide flow control once, and you provide everything once. But of course, you have to incur the complexity of doing this on different networks, on different applications, on different this and that, and you have to have very complicated logic inside this network function to know whether this application, what type of application, and so on. It's a totally different domain. So reliability is one of the top 10 listed functions in the network. Okay, reliability is one of the very important issues that's highly discussed in networking in general. So the concept talks about the fact that you have an application layer and you have transport layer and actually other layers even underneath. So whether we have a reliable channel or an unreliable channel. If we have a reliable channel, this means that this channel has absolutely no packet loss. Just imagine that. Of course, there is no such channel, but this reliable channel is 100% guaranteed that there is no packet loss. In which case, the sending process will send the data, and it does not have to do anything specific to this data because it knows that whatever it will send, it will arrive to the receiver no matter what. Okay? This is, of course, theoretical, but in reality, this does not exist. Okay? So reliability talks about the fact that if the channel is unreliable, then the sending process has to do a special thing now. First of all, I need to keep a copy of whatever I send. Why? Because now I'm not sure whether it will arrive to the receiver or not. Okay? So there is the reliable data transmission sender, which will send the data, but while sending the data, I have to keep a copy of that packet. So the packet that I'm sending, I have to keep a copy of this. Send it over the reliable channel, and now the sending process here invoked bidirectional thing. So I'm trying to send one data per unit, but from the layer point of view, now I have to send and receive. Why? Because I have to send this data and receive the reply that it has arrived. Okay? So I always have to do that. This is the overhead that I have to incur when I talk about reliability now. So for every data that I send, I have to receive an acknowledgement that it has indeed arrived to the receiver. If it has arrived to the receiver, now I kill this data unit, خلاص, I don't need it, I remove it from the buffer and I move to the next one. If the data is not received at the receiver, now I may have to, depending on the protocol, I may have to send another copy of the same packet, and hopefully the next time the unreliable channel will allow me to really send this packet through. So the sending process has initiated always a bidirectional transmission in that case. That's caused by the fact that the channel is unreliable. So if the channel is reliable, I don't have to provide reliability from my side. Okay? So you can apply this unreliable channel in every single layer. Okay? From data link layer, from network layer, from transport layer. So if I know that the layer underneath provides a reliable channel, then I don't have to do any reliability from my side. So for example, if I know that I'm using TCP in the transport layer, I don't have to provide reliability from the application layer. If I know that I'm using UDP, UDP provides unreliable channel. So in that case, you may have to provide reliability from the application point of view, which means that the application will have to do this. Will have to do this bidirectional, send, receive acknowledgement, and so on. Okay? So TCP knows that the network layer does not provide reliability, so it has to do reliable communication from its side. IP knows that data link layer provides reliability, point to point, so it does not have to provide reliability, and so on. Okay, so you can think of this as for each layer. So the characteristics of unreliable channel will determine the complexity of the reliability. This is a very important statement. Because if I know that the underneath layer provides a very unreliable channel, for example in wireless مثلا, wireless is very unreliable. So in that case, the complexity of providing reliability from a certain layer becomes more complex, becomes high. Okay? Whereas reliability from Ethernet point of view is relatively simple compared to wireless or compared to 802.11. Okay? So it depends on how unreliable the channel is. The protocol may have to be highly complex or less complex in terms of providing reliability, because reliability can be done in multiple ways. First of all, how can I detect that a packet is lost?
As in TCP,
Yes, on the TCP level, let's say.
based on the acknowledgements.
Based on the acknowledgement, bravo. مظبوط كده. Okay, so what detects that the packet is lost is actually the sender. It's always the sender, right? Is there any other way to detect that there is a packet loss?
And application layer, if they are not.
For example, by the receiver, can I detect that there is a packet loss by the receiver?
Yes.
You have like number of each packet. So if one of them is lost.
Bravo عليك. Bravo عليك. Yes. So that's another way. So I have a certain packet sequence. If the receiver knows that I received packet 3, but I did not receive packet 2, so packet 2 must be dropped or must have been lost. So I may, depending again on the protocol, I may or may not send a negative acknowledgement in that case. Even if the sender still waiting for an acknowledgement, I can cut this wait time short by sending the sender, saying to the sender that don't wait anymore. I'm telling you that the packet has been lost, so send it again. So this, in some cases, may enhance the performance, right? Because the sender may wait forever. The sender may wait for a very long time for that acknowledgement. So rather than keeping the sender waiting, I can tell the sender, don't wait too much. I'm telling you that this packet has been lost. So this will allow the sender to retransmit the packet fast, in which case this may actually enhance the performance. Okay? What is the other method? Well, the receiver may actually receive the packet, but through the decoding of this packet, it realizes that this packet arrives but in error. And that happens not in TCP, that happens in data link layer. In data link layer, the data link layer protocol has some error detection codes. So even though the frame arrives, but through this error detecting codes, I can detect whether this frame has an error or not. If the frame has one bit in error, this means that the whole frame is unusable. In which case, I can also invoke a negative acknowledgement back to the sender. So there are multiple ways, okay? And again, depending on how unreliable the channel is, the complexity of providing reliability may be high or low, okay? Depending on how unreliable the channel is and depending on what type of performance I really need. Because in certain situations, providing high complexity and reliability provides better performance. Okay, so increasing the reliability will actually enhance the performance, versus if I lower the complexity, it will still work, but in less performance. Okay, so I can be highly complex or less complex depending on these factors. Okay, so reliable data transfer. So we have reliable data transfer sending process, which is what we have initiated by sending the data here, and you have unreliable send and receive process here. Here, this is an unreliable send and receive because it actually receives bidirection. So it has implicitly the concept of reliability through receiving the acknowledgement. So it has to send and receive acknowledgement for each packet that it sends. If the data arrives to the receiving side on the reliable data transfer receive, then the the receiver side will send an acknowledgement back. Sometimes the packet is lost due to the fact that the acknowledgement did not arrive to the sender. What is the consequence of this? We'll see. We'll see a scenario that explains this. So this receive is called when the packet arrives on the receiver side. So on the receiver side, if the packet arrives, then I send an acknowledgement back, and then I send this data up to the higher layer. So the higher layer will receive this. It does not have to send the acknowledgement back. خلاص. I already sent from this side, I already sent the acknowledgement. So when I send data to the upper layer does not have to send an acknowledgement again. Okay? So this will be described through, يعني احنا we'll go through a little bit more depth into how to describe a transport protocol using what we call finite state machine. Okay? I'm not sure if you're familiar with finite state machine, but we'll talk about it next time, inshallah. So we divide the network into, or divide the scenario of sending and receiving reliable data transmission into states, and then each state will be represented using this circle, and then the state may change depending on certain events. Depending on certain events, I will branch out from this state into a different state. And depending on what event happens, I may have to move to another state or circle and stay in the same state, depending on the type of event that happens. So finite state machine is of course a very powerful tool in representing any complicated functionality in any system, not just in networks or in transport layer, in any system. Okay? So we'll talk about this next time, inshallah. So in the remaining part of time,